I'm sure you've all heard the big story this week from the US, the so-called Nuclear Ignition Facility, which announced that they had attained ignition of nuclear fusion. What does that mean? Essentially, it's been something that's tried before. Nuclear fusion, of course, as opposed to fission, which is the most common approach now in all the nuclear plants, where atoms are broken under certain conditions, to release the energy of the molecular bonds and or between the particles, and that produces a lot of radioactive waste and so on, and it is not as infinitely self-sustained as nuclear fusion, where you fuse together two atoms or molecules to form a new molecular atom and release that energy. But this also requires certain conditions under which the fusion happens. Of course, all the stars we have that are functioning still are basically fusion factories. So if we just go to our own sun, it is constantly fusing hydrogen into helium. Helium is heavier, so the gravitational pull increases, and the energy released from the fusion of hydrogen increases the thermal energy. So the volume or the sphere which the sun is keeps expanding despite the increasing gravitation. So sun has been constantly expanding and luminosity has been increasing during its lifetime of 4.6 billion years. It was 30% less luminous, which you have discussed elsewhere as the faint young sun paradox. But this idea of gravity is important because that keeps the so-called plasma. Everything is at millions of degrees centigrade, something like 27 million degrees centigrade, or beyond that up to even 100 million degrees, at which all the material is ionized and it's in a plasma state which is very light, and it can just fly away and dissipate its energy in an uncontrolled fashion, whereas the gravitational pull that continues to increase manages to hold the plasma in a shape that allows continued fusion, and the energy just escapes in the electromagnetic spectrum that we receive from gamma rays, X-rays, all the way to visible, into near infrared, microwave, radio wave, and so on and so forth. So this is the same problem we have in the fusion factories that we are trying to build on Earth. So the first discussion here is of the new news is that they somehow created ignition, which means some energy was put in to create fusion, and fusion happened and it created some cascade of reactions which released more energy than was put in to ignite the fusion. So that's the main idea. The US National Ignition Facility, here shown as target chamber, is the size of 3 American football fields. So it's 100 feet in length or more, 120 maybe, including the end zones, and whatever, 50 feet or so wide. And what they do is they focused 192 laser beams onto a target the size of a pencil eraser to initiate fusion. This is a figure from 2021, when the first shot or the first experiment was done to achieve ignition, but it was not something that was able to be reproduced. So they have changed the experimental design, they have increased the power of the lasers being used, and now they have replicated fusion again and again. So they basically take a little gold cylinder in which they put frozen deuterium and tritium hydrogen isotopes, and then they bombard it with these 19 lasers without worrying about the energy that takes to produce the lasers. The energy put in is about 2.05 megajoules, and the fusion happened. Helium was produced, cascades of reactions collapsed this little pea-sized gold cylinder to show that energy was produced, and 3.13 megajoules was produced, 54% more energy that was put in, which means if this is successful, then you can have sustained self-sustained fusion reactions, just like what happens in stars like the sun. And where do we go next? This is the big question, because this is a huge step in terms of achieving ignition to get more energy than you put in, without considering the energy of the lasers, because if you have sustained fusion, then obviously will produce infinite energy, and it's easy to contain that because you can reduce the temperature of the plasma, unlike nuclear fission where you can have some dangers. So there are many other issues that have to be considered in terms of going from this little step of ignition to making it actual energy production at scale, let's say, to get rid of the carbon-based energy sources and make this clean energy without releasing carbon. So there are many details. Why do we use deuterium and tritium? Because these are the elements that fuse at a lower temperature, produce a lower plasma, lower temperature plasma, which makes it easier to control. As we said, plasma can begin to fly away, so you have to somehow control it to have sustained reactions. So controlling plasma is a huge challenge. There are many approaches being used, as we will see in a minute, and those are not mastered yet in terms of having sustained control of the plasma and sustained fusion reactions to produce enough energy. The other thing to worry about, we will see in terms of deuterium, tritium versus other elements for doing nuclear fusion, which also turns out to be important. So in other words, there are many issues to go before we can make this utility scale or even compact fusion reactors and so on and so forth. This is a figure from this big think, which is reporting on the same news of ignition at NIF. The most straightforward and lowest energy version of the proton-proton chain, which produces helium-4 from the initial hydrogen fuel in stars, including the sun. Note that only the fusion of deuterium and proton produces helium from hydrogen. All other reactions either produce hydrogen or make helium from other isotopes of helium. There are issues associated with each of those. The fusion of deuterium and helium-3, or more rarely of deuterium with deuterium or helium-3 with helium-3, can also release energy and produce helium-4, as can occur during inertial confinement fusion. So inertial confinement is referring to this plasma control, where you can increase the density of plasma using some methods like shock waves and so on, which is what happens in some stars. And then that higher density allows the plasma for a minute to, for a fraction of a second or whatever, to stay in its shape, so that you can then sustain the reaction. So you have two hydrogen atoms merging, releasing energy to produce hydrogen molecules, which combines it. Another hydrogen produces tritium and some energy, and then that goes into another tritium coming from this side and produces hydrogen and helium. So you can just follow the reactions. And when helium and deuterium are used this way, most of the energy is produced in neutrons, which are neutral. They don't conduct, so you have to capture their energy by confining the bombardment of neutrons with a container and use that heating of the container to make water into steam and drive turbines and so on. But eventually the container gets so hot that it gets radioactive, so there are those issues to worry about. Just to add a few more details, what are the fuel mixes? Many reactors fuse deuterium with tritium to release energy. Deuterium plus tritium giving you helium plus a neutron, as we just said. This mix ignites or creates a self-sustaining fusion reaction at around 100 million Kelvin. It produces neutrons which can make the chamber radioactive, as I just said. Other reactions such as fusing proton with boron 11 don't produce neutrons, but ignition requires higher temperatures, so the plasma temperature is much higher and so on. And then plasma controls have other methods like using magnetic fields to contain the plasma, control the plasma. There are newer methods about swirling them, using vorticity to control them, and so on. And there are methods to improve the regular magnetic fields, which require helium cooling, which is very difficult. Liquid helium is very hard to contain because it leaks out. So high temperature magnets, on the other hand, can be cooled with liquid nitrogen, which is much more abundant, etc. So all these various pros and cons have to be dealt with. Looking at some other details from this Nature article meant for general audience, the other methods of trying to contain plasma include things like tokamak, which is like this donut-shaped container. So superconducting magnetic coils cooled by liquid helium hold plasma in a toroidal vessel. So you have the magnetic coils and the plasma flowing around here to be contained. But as we said, superconducting magnetic coils require liquid helium, which is hard to manage. And there are mini tokamaks. So Tokamak Energy, Commonwealth Fusion Systems, and others are using this. There are many commercial ventures. We'll see how much capital is flowing into those. Magnets made of high temperature superconductors produce stronger fields and can be cooled more easily, allowing more compact spherical tokamaks to be built. So this is heading towards commercial small scale fusion reactors, which are getting a lot of airtime as well in terms of how the energy problem can be solved more affordably, more earlier, as we will see the price range in a minute as well. So this is the linear colliding beams reactor. So this is used by TAE Technologies, another company. Packets of plasma are fired into a central chamber and rotate rapidly inside a solenoid, the coiled wire electromagnet. So that's how you would control the plasma in this case. And here are the fuel beams, and here is a central chamber. So this is another way to control the plasma. So that's a big step, going from this ignition that has been accomplished to actually making functioning plasma fusion reactors. So Fusion Rush, this is the firms and governments that are developing many kinds of fusion reactors. They all heat gas to create a plasma confined at such high temperatures that atomic nuclei fuse, releasing energy that can be harnessed for electricity. Here are 5 prominent designs. So lots of money here, and the idea is that just like the COVID vaccines, with these many resources, this can go forward very quickly and get here in time for us to decarbonize and get to our global warming targets. Cross your fingers and, hope for the best. Magnetized target reactor. This is used by General Fusion. I think it's a UK company, which shows a lot of promise. A spinning ball of liquid metal confines plasma. Pistons then rapidly compress it. The plasma is allowed to expand and then compressed again. Okay, so there are the pistons, there is the spinning ball, and there is the liquid metal, and so on and so forth. These are all attempts to control the plasma. Again, these are steps after ignition happens. Stellarator. This is from Wendelstein 7X. A complicated twisted loop of magnetic field confines the plasma. Did I miss something? No, okay. So future funding, I think I might have misplaced. Oops. No, okay. We are good. We already looked at these. So, oops, am I going in the wrong direction? Yeah, I just somehow reintroduced that slide. Okay, so fusion funding. Private fusion firms have disclosed more than 2.4 billion in funding. This is still not to scale them up to usable reactors at scale. TAE Technologies comes in at $880 million of funding they have received. Helion Energy at 578, Commonwealth Fusion Systems 250, General Fusion 200, Tokamak Energy at 200, and other 12 firms altogether at 312. So the idea is that with this kind of funding, the fusion research and functional fusion reactors are on their way. So fusion promises in terms of time scales expected. Private firms are making bold promises about delivering commercial fusion reactors in the 2030s. A lot of people are very skeptical about this, but just looking at private and state-sponsored fundings. Helion, net electricity, small amounts from Polaris reactor without going into technical details. Giant international effort under ITER. Test runs, so state sponsored, and then there are Commonwealth fusion systems. First fusion machine expected to generate more energy than it uses, literally like the first flight of the Wright brothers. And if you look at the speed with which the research in flight has happened, it is astounding. But in this case, we need energy much quicker than that. General Fusion operate UK demonstration plant. That's by 2020. I hope I didn't misplace this. Yeah, this is all by 2020. This is by 2025. By 2030, also TAE Technologies reactors ready for commercialization by the late 2020s. Going to 2035, we expect CFS, which is aiming to have 200 megawatt plant supplying electricity grid in early 2030. So this is already expected at scale to feed the grids. General Fusion targets reactors for sale in early 2030s. First Light Fusion anticipates its first power plant in 2030s. Tokamak Energy Fusion power plant pilot is expected in 2030s. ITER to run fusion by 2040. ITER to run fusion with deuterium and tritium fuel. China Fusion Engineering test reactor might complete construction in 2030s. UK Atomic Energy Authority hopes STEP fusion power plant can supply energy to national grid. This is, I think, an acronym, some kind of a sustained something energy production or such that you can look up. Okay, so that just tells you that the news on ignition is a great first step, but it's something to watch for in terms of how the other steps of getting to feeding into grids and nuclear fusion reactors are going to come along. But it's not that every company will use the same fusion approach, because same ignition approach, because how the ignition happens is not at all critical in terms of sustained fusion reactions with plasma controls and so on, and how to extract energy from them and which fuel will be used, etc. There are details of how helium-3 is very difficult to make. It's found in Moon, for example, so it's not very realistic to produce and use on Earth, but boron, hydrogen and other combinations will probably end up being used. And once the plasma control technique is established, then higher temperature plasma fuels like boron probably will be used, because even though they function at higher temperatures, produce higher temperature plasma. If they can be controlled, then their energy is not in neutrons, that you can actually more easily convert it and reduce the radioactive emissions that you will get from the container of the neutron energy produced by deuterium-tritium fusion, which we just talked about. Okay, so just a brief introduction. There's lots of very interesting literature that you should follow up if you're interested in this. I'm obviously not a nuclear physicist nor a physicist of any sort, but I wanted to do enough research to put this simple podcast together, because this is really directly related to decarbonization and reaching global warming targets of 2 degrees or 1.5 degrees and so on. Other than, of course, having a good energy source, there are issues of equity, access, justice and so on, which we'll have to deal with at a later stage if these become functional and so on. Okay.